let's start with. Okay, let's go through these 6. I asked you which ones are electrophiles and which ones are nucleophiles. I didn't change the second one to include all the answers. So, what about A? What's A? Electrophile or nucleophile? Electrophile because it's electron poor with a positive charge. B. Nucleophile. What makes the oxygen electron rich? Lone pairs. So it doesn't have to have a negative charge, it just has to have lone pairs to be electron rich. CH3, CH2 minus. Nucleophile because the carbon's going to have a lone pair to make it have a negative charge. Okay, how about the oxygen and the carbonyl? What does everybody else think? Nucleophile, electrophile? Nucleophile. The carbon. What?
I said I think it's an electrophile because it's attached to the oxygen. So
okay, and so because the carbon's attached to the oxygen would be slightly minus and the carbon would be slightly plus in terms of a polar covalent bond. And so that's going to make the carbon with the delta positive electron poor, which makes it an electrophile. How about F?
The carbon is the electrophile, right?
Yes. The oxygen would be nucleophilic, and the carbon of the carbonyl will be electrophilic. In F, the carbon that's attached to the bromine. Electrophilic, because the carbon is attached to the bromine. The bromine's going to pull electron density. It's going to become delta minus. The carbon then will be delta plus. Electron poor, it'll be electrophilic. And then the double bond. Nucleophile? No? What do you think?
is there non-polar?
No, there's either electrophile or nucleophile. That's it. So you only have those 2 choices. Nucleophile. So what makes the double bond electron rich? The pi bond. So the fact that it has a pi bond that it could donate that pair of electrons to and not break the bond makes the double bond nucleophilic. Okay. So that G is nucleophilic as well. Okay. Right. So next one. Reaction coordinate diagram. Okay, which reaction below the red, which is the upper one, or the green, the lower one? Which one of those which reaction is going to occur faster? Green. Okay. Why? Because it has the lowest activation energy. And so the Arrhenius equation tells us the rate is proportional to, it's proportional to a logarithmic function of the rate of the activation energy. So lower activation energy, faster rate. For the same diagram, which reaction, red or green, produces the most stable products? Green. Green is correct. Why? Because on any energy coordinate diagram, the lower energy you are, the more stable you are. So the green reactions producing C and D, which has a lower overall energy than does E and F. So the green one also, in this case, produces the most stable product. And then carbocation stability. Which one is number one? Most stable is C, then A, and then B. Tertiary, secondary, then primary, and we're not even going to draw primary carbocations this semester. Okay. All right, any questions about any of those? Okay, so those are kind of the fundamentals. We'll talk a little bit more about the reaction coordinate diagram, but I want to finish up talking about the reactions where we left off on Monday, and that was we were talking about we were talking about the one-step reaction where we had in step one, we reacted a tertiary chloride with hydroxide. And in elementary step one of the mechanism, we broke the carbon-chlorine bond and we formed a carbocation, which is a carbon with a plus charge, and then also formed the chloride ion. Okay. So that was elementary step one. Then once we formed the carbocation, which is the electrophile in this case, it reacted with the hydroxide ion, the hydroxide donating its pair of electrons to the carbon to produce the final product, which was the alcohol. So, which one of those two was the slow step? The top one? Do we agree? Okay, so this was the slow step, which is also called the rate determining step. And then the second step is relatively fast. So the reaction is going to wait for the formation of carbocation. When we form the carbocation, then the nucleophile immediately adds. So in terms of then the reaction coordinate diagram, we have how many intermediates? One, and the intermediate is the carbocation. So we've got a transition state to get to the intermediate, and then another transition state to get to the final product. So there's our reactants, our products, our carbocation intermediate, and then our two transition states. And we should write the structure of the transition states just to get practice doing that. So for the first transition state, what happens? Well, what is a transition state? What happens in a transition state?
Highest energy.
It's the highest energy, but what's happening, David? Bonds are being broken and made and broken. That's what you were going to say? Okay, that's where the bonds are being made and broken in the transition state. So how am I going to show the transition state for the first step? And I left blanks there so that I could put them in. Well, first thing we're going to do is we're going to draw kind of the average structure of the reactants and the products. So I'm going to draw it like that. Which bond is being broken? The carbon-chlorine bond. So how am I going to represent that in the transition state? As a dotted line hash, not as an arrow, but as a dotted line. Because a dotted line means what? It's a partial bond. So I've got a partial bond between carbon and chlorine. Now, either way I go in this reaction, from left to right or right to left, if I'm breaking the bond or I'm making the bond, same transition state. The bond is partially formed. Now I've got to average the charges out. So in the left, both the carbon and the chlorine are 0 formal charge. And in the right, the carbon is +1. So the average of 0 and +1 is? What is it if I don't want to know it exactly numerically? What's between 0 and +1?
Yeah, so it's 0.5.
But I don't necessarily actually know that. That's if it was at perfect 50-50 in the reaction. I don't know that that's the case.
Right, partial charges?
Okay, so I can have a partial charge just like I can have a partial bond. So what do we write a partial charge with? A delta. So the carbon's going to be delta positive in charge. And then what's the chlorine? With an average between 0 and -1, it's going to be delta minus. So in the transition state, the carbon is getting some positive charge and the chlorine is getting some negative charge. It will get the full-blown +1, -1 after the reaction occurs. So when we write the transition state, it's actually an average of the two structures on either side. And we average bonds and we average charges. This is exactly how we would write the resonance hybrid. We would take the average of the charges and the average of the bonds in the resonance structures. So this is exactly the same thing. Okay. So what would the transition state for the second step look like? Because I left space for it. What kind of bond?
A dotted line.
Okay, so a dotted line between the carbon and the oxygen, and just shout it out. The OH would have a delta minus and the carbon a delta plus. A delta plus on the carbon. Same thing. Because actually when you're forming a bond, it's the opposite of breaking the bond. So they look very similar. They'll have different energies because it's a chloride versus a hydroxide. So that's this complete mechanism. And we knew that because when we looked at the rate equation, the overall rate equation was K times concentration to the alkyl halide to the first power. And when we changed the nucleophile's concentration, the hydroxide, nothing happened to the rate. So that means its concentration was to the 0 power. It didn't show up in the... And so so this mechanism where we've got number 1 and we've got number 2, the first step gives the same rate equation, and so therefore that's the rate determining step. And that's where we were at like 3 minutes before the end of class. Then we went on to say, okay, how about how about the physical property of the intermediate, the carbocation? And it's an intermediate, so it's not very stable. What we said was a C plus species is only going to have 6 valence electrons, and that's far from 8. So what I need to do is to push electron density into that carbon to get it closer to 8. It will never ever be 8, but the closer I can get it, the more stable it'll be. So then we recognize that in a carbon-hydrogen alkyl group, that the carbon is less electronegative than the carbon, and so that means that all the hydrogens are slightly positive, all the carbon is slightly negative, and so every time you have an alkyl group, that carbon has a little bit of electron density extra. And what it can do is it can now donate that to the carbocation and get it closer to 8. Maybe 6.2, 6.3. But the critical part here is if I want to make the carbocation more stable, maximize the number of alkyl groups attached to it. So put 3 alkyl groups would be more stable than just having 2. And if you only have 1, it's not going to form this semester. We don't have primary carbocations in solution at room temperature. Okay. And that was the first thing that people wanted to know, was about the tertiary carbocations. Is that the most stable? And it is. All right. So we're all on the same page? Because now I'm going to ask a question. I'm going to do 2 reactions. I'm going to take the hydroxide and I'm going to react it with 2 different alkyl halides. I'm going to react it with isopropyl chloride and I'm going to react it with tertiary chloride. And I'm going to stipulate for this reaction that they both occur by the 2-step mechanism. So they both occur by what we call Sn1. That's unimolecular, which means it was the 2-step mechanism. Because if they go by different mechanisms, it's like comparing apples to cars. You can't. So I couldn't compare an Sn2 mechanism, the 1-step that we talked about on Monday, to the 2-step. I can't talk about the rates because it's a different mechanism. So here I'm going to say these both go by Sn1. Okay. And I'm going to make this a multiple choice question. So my question to you is, which reaction occurs fastest? A, B, or C, they occur at the same rate. And so there's no right or wrong here. Discuss with a neighbor, and then vote and tell me what you think. Okay. What's your gut instinct on this? Right? So you've got a minute for the moment, maybe 2 minutes.
Wait, is it on here? Yeah.
You could use I don't know for D, but I'd really like you to give me A, B, or C. That was quick. The volume goes up when everybody's discussing, and then it just drops off. Okay, vote.
I really texted the thing and it said my thing wasn't valid.
Well, don't text. Just answer the question with the app, if you've got it. I don't know anything about the texting. For all we know, that could be a Canadian number. I don't know if you have to set up the text link to your account or not, because otherwise it wouldn't know what your phone number is to count it. Okay. You got to make a guess. There's 26 people here. If somebody's waiting at home for this to come out, they should really just be here. Okay, we're done. No, we're not done. Okay, so let's see what we say. Okay, we've got 16 A's, 9 B's, 1 C. That's 26. Okay? So, there are no wrong answers here, so do not be afraid to throw out your reasoning to the class. I'm not going to humiliate anybody. I may take your answer, and if the reasoning's perfectly fine, then it's a possible reason for this. But what I'd like to know is, what was your reasoning for choosing A? Someone who chose A.
One of the parts of the discussion is that because it's only a secondary carbocation, it would have a higher reactivity in the second part after you put the amount of application energy in. I think that it would fall faster because it really wants to get the electrophile onto it.
Okay. And it would want to get the hydroxide in the second step more than the tertiary because of why?
It is not being balanced as much as the tertiary because it would have a 6.1 compared to
Okay.
a 6.3.
All right. So the carbocation, the secondary carbocation is more unstable,
Yeah.
which would make it more reactive in the second step. Okay? I'll accept that reasoning. That's sound reasoning. There's no flaw there. That's accurate. What did you just say?
The rate determining step is the second one.
I'll accept that one too. I'll accept that as a sound statement as well. That the rate determining step is the first one.
I picked B, and I think B is more stable than it would be less likely to react, so it would be the slower step.
Okay, so because the tertiary carbocation is more stable in terms of the rate determining step, what does that mean?
It would be slower because it would take more to form treatment.
So the rate determining step for the tertiary carbocation would be slower. Okay. And so you chose B.
Yeah.
Okay. Okay. What other reasons?
Indeed, since tertiary activation energy would be lower, resulting in more stable end result.
Okay. So because it's more stable, it'll have lower activation energy?
Yeah.
Okay. I'll accept that as a sound statement of fact. Did you raise your hand? Okay.
I said B because the tertiary carbon is gonna be more stable. And at the beginning it said that the more stable products are gonna have a faster rate, so.
Okay, so the more stable products are going to have a faster rate. Okay. I'll make that a half of correct statement, because sometimes that's the case and sometimes it's not. Anything else? Okay, so, and we haven't done this yet, so it's just kind of getting an idea of how good your gut instincts are. They're about 50%, a little less than 50%. But here's what we have to think about. So what we have to think about is the following. What's called the Hammonds Postulate. Let's see, where did all my papers go? I have a piece of paper, which I can turn into a reaction coordinate diagram. Okay, so reactants, products, transition state, because I'm going to look at the first step of the reaction, the rate determining step. So my alkyl halide going to my carbocation on the right, on your right. So if it's thermoneutral, the transition state is dead in the center. In other words, if it's not exothermic or endothermic. If the reactants and products have the same energy, transition state's right dead smack in the middle. Now, notice what happens when I make the reactant or make the product more stable. What happens to the activation energy? It decreases. Now, that's not what Hammond said. Hammond said that when the reaction becomes more exothermic, that the transition state begins to resemble more the reactants than the products. That's actually what Hammond said. And if you think about that, if we're going from a reactant to a transition state, the less changes in structure that we have to make, the quicker and less energy it'll take, which is the activation energy. So when the transition state looks more like the reactant than the product, you're going to have a lower activation energy. And what we're talking about is taking a secondary carbocation that might look like this one and making it a tertiary carbocation. And so the tertiary carbocation's activation energy was what relative to the secondary? If I draw my diagram so it looks like this, and so it looks like that, here's my secondary carbocation, here's my tertiary carbocation, and so what happens? The tertiary carbocation has a lower activation energy. That's not drawn to scale, that's just trying to give you the general idea. Actually, the diagram, the red and the green one that I gave you at the beginning, that would be the perfect one to use. So the lower the transition state, the more stable the product, the lower its transition state energy. Okay? And so that's how we interpret Hammonds postulate. So anything I do to make the product more stable, that's going to make the activation energy lower. And because the Arrhenius equation says that the rate is equal to A e to the minus EA over RT, the lower then mathematically, the lower I make the activation energy, the faster the rate. So that's the key. You form the more stable intermediate, or you form the more stable product depending on the mechanism. If this was a one-step mechanism, the more stable the product, the faster it's formed. Now, if it's a multiple-step mechanism, we've got to look at the rate-determining step. Which is why when you said, but the rate-determining step is step 1, that was the most critical statement. Because what happens in step 2 is irrelevant. Because it's step 1 that's the rate-determining step.
What is the definition of a postulate again?
So basically, the more stable the product, the lower the activation energy. And that's how we use Hammonds postulate in organic class. I mean, we're reinterpreting it for him. So for the SN1 reaction, if I go back to the to this one, which one's going to go faster? That's going to go faster. Why? Because I'm going to form a tertiary carbocation faster than a secondary carbocation. And the second step doesn't matter. So forming a secondary carbocation, even though it's less stable, well, that means that it would react faster in the second step, but the second step isn't the rate-determining step. It's the formation of the carbocation that's a critical part. Okay. And that's what Hammonds postulate lets us do. All right. So, we're okay with that?
What was the answer B?
The answer was B. Now, this morning I asked, and I got some other creative answers, which were true statements, but didn't quite get at that answer. And somebody talked about the number of groups around A. And that with having 2 methyl groups versus 3 methyl groups, the hydroxide would be able to come in and attack that carbon easier than it would with a tertiary. Absolutely true statement. So if you thought of that, absolutely true statement. But is it relevant for the two-step mechanism? No. It is relevant for which mechanism, though? The other one. The one-step mechanism where the nucleophile has to come in and kick off the chlorine. So when we talk about the Sn2 mechanism, which was the one-step, there, a primary halide reacts faster than a secondary halide, which reacts infinitely faster than a tertiary halide, because a tertiary halide has too much stuff for the nucleophile to get to that carbon. It can't.
Wait, I have a question just about the SN1 and SN2. Where's the number from again?
So the number here means that this is unimolecular kinetics. And unimolecular kinetics means that it was a two-step process where the alkyl halide breaking apart was the rate-determining step. The SN2 means that it's a one-step mechanism because it's bimolecular kinetics. The bimolecular kinetics, and that's where the nucleophile comes in and directly attacks the alkyl halide and kicks off the halogen. So I'm trying to use more one-step, two-step, because that's what the book uses, because we haven't, well, we are being formally introduced to SN1 versus SN2, but I tend to use that as my first thing, so it's really one step and two steps.
So if we were doing the one-step mechanism, the top one would be faster?
Yes.
Okay.
Yes. But here's the thing.
You couldn't really do it with the second one, could you?
The second one, so what happens is when you have a primary alkyl halide, it reacts faster in the one-step mechanism. But the tertiary one can't undergo that reaction, but then it has an alternative pathway. So then it can break the carbon-chlorine bond, form the carbo-cation, and react that way. So all of these can still undergo nucleophilic substitution, but the mechanism changes because primary alkyl halides can't do two steps because they can't form a carbo-cation. The tertiaries can't do a one-step mechanism because they got too much stuff around the carbon. So they're kind of fixed. They're either one or two steps. Now the secondaries are in between, and that's where there's a lot of gray area. Because the secondaries can do either one. And when we define our rules later on, we're gonna over-define them and make them straightforward when they're really not. Because the secondaries can create all sorts of anomalies. And when there's enough anomalies, you begin to question whether the rules are even true. So the first year I taught at Kansas State, I taught the dietitians and the vet students organic, which was one semester. And then some other guy taught the 2-semester pre-med. And he said, he goes, this SN2, SN1 stuff, he goes, I don't even know if I believe what we're teaching them. And I said, that's because you're focusing on the anomalies, not the stuff that works all the time. Because if I taught you the anomalies, you would have no idea what's going on. So that's why we make it simple. One step, two step. This is going to depend, but let's wait a couple weeks and talk about that. So if you were thinking about the bulk, the number of alkyl groups around the carbon, good thought. It's just that we apply to the one-step mechanism, not the two-step. So that's what we need to think about in terms of the intermediates. So Hammonds Postulate basically just says if we make the products more stable, whether those products are true products or whether they're intermediates, they're going to lower the activation energy and the reaction's going to go faster. But Hammond didn't say anything about a faster reaction. Because in order to do this, you'd have to say Hammond's postulate says lower the energy of the product, lower the activation energy. Arrhenius equation says lower activation energy, faster reaction. So then, I don't even know if I should do this, but I will. Because let's say you start, and I'm going to make this totally generic because this is like a second semester topic, but they introduced it in the book Kinetic versus Thermodynamics. Let's just go through very quickly. Let's say I'm in the middle. And this is an intermediate. We'll call it a carbocation intermediate, although it's got to be a special one. And to its right, it sees a transition state and then a final product. Because, to be honest with you, molecules are not on a highway. They're not on the reaction coordinate diagram that's just a highway. You either go this way or you go backwards. They're like, I don't know, they're in the middle of an intersection where all the highways come to them. And so the other example is they're in a valley surrounded by mountains. And so if they go this way, there's a mountain. If they go this way, there's a mountain. If they go that way, there's a mountain. And those mountains are the transition states. And then on the other side of the mountains that they can't see are the products. And so if you're sitting here in between a transition state going this way or going this way, you're stuck. It's people letting students out 3 or 4 minutes before the end of class. Should be 3 or 4 minutes after class. First question, and then we'll finish this up. Then we'll finish this part up on Friday. Which way is faster? To go to the left or go to the right? Left, because lower activation energy. Okay. But if I go to the left, am I forming the most stable product? According to this diagram? No. Is that a problem? It depends. So when I have a diagram that looks like this, where the intermediate can go both ways, if I said, well, what's the major product of this reaction going to be? My answer is, it depends. On what? Well, it depends on whether I'm doing the reaction for a short or long period of time. It depends on whether I'm doing this reaction with a lot of energy or with a minimum of energy. In other words, low temperature or high temperature. And we can understand how this works, but not in no minutes. So on Friday, we'll take up this idea just to help reinforce the idea of what does it mean for the activation energy, what does it mean for the more and less stable product.
Is there a reading for today?
Yes.
Is
It was the rest of chapter 3.
For today? No, like do Friday.
So for Friday, it's going to be the first few sections of chapter 4.
Is that online?
I have not released your chapter 4 yet. I will do that in a few minutes. And I won't put in, and when I release it, I won't put an expiration date on it yet. I'll put in the dates everything's due, so it'll be next week. Okay, so it'll be the first part of chapter 4, but we will go back and we'll finish this topic up, because on Friday at midnight, that's when the in-reading problems are all due.
So chapter 3 is due on Friday.
So chapter 3 is due on Friday.
So in lab last Thursday, they wrote on the board like things we should include in our lab
Hammonds board things, and on the board they wrote Lab 3B due 9/27, which is next Thursday.
Okay.
And I didn't know if that should be different since I'm in Dr. Simmons' lab, or if it should be due tomorrow. Because on Canvas it says it's due tomorrow, but like in lab they wrote on the board it's due next.
In Dr. Simmons' lab.
Yeah.
Well, then I guess you're bound by Dr. Simmons' rules,
Yeah.
not by mine.
But like on Canvas it's still 20th.
Well, you have an out because you can tell her
Okay.
that. Yeah.
Okay.
But my intent was that it was going to be due